Bismillahirrahmanirrahim. In lecture 1, we have learned the basics of heat transfer, that what is heat transfer, what are the different modes of heat transfer, and we have found that there are three modes of heat transfer, which are conduction, convection, and radiation. We have learned the rate equations, which deals with the conduction, convection, and radiation. In lecture 2, we have done the problems related to simple rate equations of conduction, convection, and radiation. Now in lecture 3, we are going to start the detailed discussion about the conduction. In this lecture, we will learn the how the conduction rate equation comes into an existence. We will learn the different thermal properties of the material, and finally we will learn the heat diffusion equation in Cartesian coordinate system, in cylindrical coordinate system, and in spherical coordinate system. First, we are going to discuss the conduction rate equation, which is also known as Fourier's law. Consider we have a cylindrical rod of uniform cross-sectional area A and length delta x. The left side of the rod is maintained at temperature T1 and right side of the rod is maintained at temperature T2 such that T1 is greater than T2. It means that left side of the rod is hotter than the right side of the rod. So heat will flow from left side to the right side as shown in this figure. If the lateral side of the rod is perfectly insulated, so heat will flow only in the longitudinal direction and no heat will flow in the lateral direction, or heat will flow only in the x direction as clearly witnessed from this figure. Now we are going to check how heat transfer varies by varying temperature difference, length of the rod, and the cross-sectional area. What are the dependence of heat transfer upon temperature difference, length of the rod, and cross-sectional area? First, we are going to keep temperature difference and the length of the rod constant, and we are varying cross-sectional area. If we vary cross-sectional area, then we will find that heat transfer is directly proportional to the cross-sectional area. It means that when we increase the cross-sectional area, heat transfer will increase, and if we reduce the cross-sectional area, heat transfer will decrease. This can be understood by imagining that you are traveling on a road. The traffic flow can be compared with heat flow. If the road is wide, then traffic flow will be high. As the bottleneck occurs on the road, traffic flow will be reduced as low area will be available for the traffic flow. Same is applicable for the heat transfer. Hence, heat transfer is directly proportional to the area available. Now we are going to keep temperature difference and area constant, and we are going to vary length of the rod. As length of the rod is increased, we will found that heat transfer decreases. It means that heat transfer is inversely proportional to the length of the rod. Finally, we are going to keep area and length of the rod constant. Now we will find that Qx, or heat transfer in x direction, is directly proportional to the temperature difference. When the temperature difference is high, more heat will transfer. And when the temperature difference decreases, heat transfer will be reduced. By combining these conditions, we will find remember that this proportionality is valid for each and every material. Delta x. This proportionality remains valid for copper, for aluminium, for wood, for plastic, for glass, for iron, for each and every material. This proportionality remains valid. But consider we have metal and plastic of same cross-sectional area and of same length, and the temperature difference in both cases is same. We will find that heat transfer will be maximum in case of metal and will be minimum in case of plastic. It means there is some property which is influencing the heat transfer rate. So we can convert the proportionality into an equality by introducing a coefficient that is a measure of the material behavior. And we will find that Qx is equal to Ka delta T over delta x. This K is known as constant of proportionality, and this K is known as material property known as thermal conductivity. It has unit of watt per meter Kelvin. The thermal conductivity of each and every material is different. It is different for copper, it is different for iron, it is different for aluminium, it is different for wood, it is different for glass, it is different for plastic. For each and every material, thermal conductivity is different. Materials having high thermal conductivity are known as conductors, like metals, and the materials having low thermal conductivity are termed as insulator, like wood, glass, plastic, etc. This equation can be converted into differential equation. If delta x tends to be 0, then we can write qx equal to minus ka dt over dx. Here minus sign is introduced because minus sign is showing that heat always flow in the direction of decreasing temperature. This equation is known as conduction rate equation or Fourier's law of heat transfer. Throughout this course, you will use the term heat flux, and we have discussed the heat flux in the first lecture, that heat flux is the heat transfer per unit perpendicular area. Consider you are sitting in a room. Remember, heat flux, as I have mentioned, that heat flux is the heat transfer per unit perpendicular area, and it is given by qx double dash equal to qx over a, and in terms of Fourier's law it is equal to minus k dt over dx. Now consider yourself that you are sitting in a room and your left wall is maintained at a uniform temperature of T1 and right wall is maintained at a uniform temperature of T2, such that T1 is greater than T2. So heat will transfer from T1 to T2 because heat always flow from higher temperature to the lower temperature, and you can witness this in the figure that is displaying on your screen. Now, heat flux is the heat transfer per unit perpendicular area, and it is always at normal to the surface of constant temperature. Your left wall is maintained at a uniform temperature of T1 and your right side is maintained at a uniform temperature of T2. Your left wall and right wall are maintained at uniform temperature. So heat flux will be normal to the surface of constant temperature. It means heat flux will be normal to the left wall or normal to the right wall, because left walls and right walls are maintained at the uniform temperature of T1 and T2 respectively. From this, we can conclude that heat flux is the vector quantity. So, utilizing this, a more general statement of conduction rate equation, Fourier's law can be written as Q double dash is equal to minus K del T, where del is the three-dimensional del operator, which you have learned in your calculus, and T is the three-dimensional scalar temperature field. Here I, J, K written within the bracket are the unit vector in the x, y and z directions respectively, and K, which is written outside the bracket, is the thermal conductivity of the material. Remember, heat flux is the directional quantity, it is a vector quantity. Heat flux can be resolved into Cartesian coordinates, and the general expression for heat flux is Q double dash is equal to I Qx double dash plus J Qy double dash plus K Qz double dash, where I, J, K are the unit vectors in the x, y and z direction, and Qx double dash, Qy double dash and Qz double dash are the heat flux in x, y and z directions respectively. Here Qx double dash is equal to minus K dava T over dava X, or the heat flux in the X direction due to the temperature gradient exists in the X direction. Qy double dash is the heat flux in the Y direction due to the temperature difference in Y direction. And Qz double dash is the heat flux in the Z direction due to the temperature gradient in the Z direction. I hope that this have made a clear concept about heat conduction equation, conduction rate equation, which is known as Fourier's law. And in this equation, we have learned that heat flux is the directional quantity and it can be resolved into x, y, and z components. Now we are moving towards the thermal properties of the material. The first thermal property which we are going to discuss is the thermal conductivity. And from Fourier's law of heat transfer, thermal conductivity associated with conduction in x direction can be given as Kx is equal to minus Qx double dash over dava T over dava x. Here Kx is the thermal conductivity in x direction, Qx double dash is the heat flux in x direction, and dava T over dava x is the temperature gradient in the x direction. Same definition will be used for thermal conductivity in y direction and z direction. For isotropic material, I think you have learned about the isotropic material in materials that isotropic material is the material whose properties are independent of the direction or whose property remains same in each and every direction. For isotropic material, Kx will be equal to Ky, will be equal to Kz, and it will be equal to K. In isotropic material, Kx equal to Ky equal to Kz, and that can be generally termed as K. Remember, thermal conductivity is a property which tells about how much heat will be conduct when there is a temperature difference of 1 Kelvin or 1 degree centigrade exists. Materials having high thermal conductivity are known as conductors, light metals, and the materials having low thermal conductivity are known as insulators, like glass, wood, plastic, foam, etc. The insulators are used to reduce the heat loss. As you have witnessed in your air conditioner's pipe, that there's a foam wrapped up on a pipe. That foam is basically an insulator which has low value of thermal conductivity. That foam is reducing the heat loss from the pipe to the environment so that your air conditioner maintains the temperature of your room. So insulator are the material having low thermal conductivity, and insulators are used to reduce the heat loss. The materials having a high thermal conductivity are used in when there's a heating requirement, like you have to cook a meal, you will use metal rather than plastic, because if you use plastic or you use glass or wood in order to cook something, it will take a lot of time, because glass, wood, plastics all have low value of thermal conductivity. That's why you use metal for cooking a meal, because metals have high thermal conductivity. The second property which we are going to discuss is the thermal diffusivity, and it is the ratio of thermal conductivity to the heat capacity. It has unit of meter square per second, and it can be represented as alpha is equal to K over rho Cp, where K is the thermal conductivity, rho is the density, Cp is the heat specific heat capacity at constant pressure. It measures the ability of a material to conduct thermal energy relative to its ability to store thermal energy. This property tells us that either a material will conduct energy or will store thermal energy. Materials having large value of thermal diffusivity will respond quickly to change in the thermal environment, whereas material of a small thermal diffusivity will respond more sluggishly, as it takes longer to reach a new equilibrium condition. These are the two basic thermal properties of matter: thermal conductivity and thermal diffusivity. Now we are going to discuss heat diffusion equation. That what is heat diffusion equation? We have a differential control volume having dimensions of dx, dy, and dz. The heat into the cube in x direction is qx. The amount of heat that goes out of the cube in x direction is qx plus dx. of heat enters in the cube in y direction is qy, and the amount of heat that goes out of the cube in y direction is qy plus dy. The amount of heat that goes into the cube in z direction is qz, and the amount of heat that goes out of the cube in z direction is qz plus dz. Consider there is a heating element or heat generation element is placed within the cube, and the amount of heat generated is given as Eg. The cube is made up of material which can store energy, and the amount of energy that is stored within the cube is EST. I will recommend that draw this figure in your notebook, as it will give you a clear picture, and that figure will use in order to drive an diffusion equation. Uh, Consider a homogeneous material, as I have discussed that there is no bulk fluid motion, only conduction occurs when there is a temperature difference exists, and in the absence of any type of motion there are no changes as in mechanical energy and no work being done on the system. So only conduction will occur if temperature gradients occur in x, y, and z direction. The heat goes out of the system can be computed by using Taylor series if we neglect the higher order terms. And I believe that you have learned the Taylor series in calculus. The heat goes out of the system in x direction will be qx plus dava qx dava x times dx. The heat goes out of the system in y direction will be qy plus dava qy by dava y times dy, and the heat goes out of the system in z direction will be qz plus dava qz by dava z times dz. As we have mentioned in the figure that there's a heat generation element is placed within the cube, so the amount of heat generation will be q times dx dy dz. Here dx dy dz is the differential volume, and q is the rate at which energy is generated per unit volume, and it has unit of watt per meter cube. We have also discussed that the cube is made up of material which can store energy, and the energy stored can be given as raw Cp dava T over dava T times dx dy dz. dx dy dz is the differential control volume, and the raw Cp dava T over dava T is the time rate of change of sensible energy per unit volume. Now we are going to apply energy balance, and on rate basis energy input plus energy generated minus energy out will be the stored energy. E in plus E generated minus E out is equal to E is stored. The heat input to the system will is Qx, Qy, and Qz. These are the heat input in x, y, and z direction. Heat generated with the system is Q dx dy dz, as we have discussed earlier, and the heat goes out of the system are Qx plus dz and qz plus dz in x, y, and z directions respectively. The energy stored is given as raw Cp dava T over dava T dx dy dz. These terms we have discussed earlier. Now we are going to substitute the value of qx plus dx, qy plus dy, and qz plus dz from Taylor's series. And when we put the value of heat goes out of the system using Taylor's series, we will come up with equation which is uh, available on your screen, that minus dava qx by dava x times dx minus dava qy over dava y times dy minus dava qz over dava z times dz plus q dx dy dz equal to raw Cp dava T over dava T times dava dx dy dz. Now using Fourier's law of heat transfer, that qx will be minus k dy dz dava T over dava x, qy equal to minus k dx dz dava T over dava y, qz will be minus k dx dy dava T over dava z. Now this is a cube and this is the heat transfer in x direction, heat flow in the x direction. The shaded area is the area perpendicular to the direction of heat in x direction, and it is evident that the area perpendicular to the direction of heat in x direction is dy by dz. So that's why the area mentioned in the equation of heat flow in x direction is dy times dz. Same for heat transfer in y direction. This is the heat transfer in y direction. The green area is the area perpendicular to the direction of heat in y direction, and it is clear that the area perpendicular to the direction of heat in y direction is dx by dz. Similarly, you can witness that the area perpendicular to the direction of heat in z direction is dx by dy. When we put the value of qx, qy, and qz in the equation that we drive by substituting the values of heat goes out of the system, we have come with this equation which is uh, available on your screen. Since dx, dy, dz are common on both sides, so we can come up with equation dava by dava x times k dava t over dava x plus dava by dava y times k dava t over dava y plus dava over dava z times k dava t over dava z plus q is equals to raw Cp dava t over dava t. dx, dy, dz are cancelled out from both sides, and we have come up with general equation, and this equation is known as heat diffusion equation in Cartesian coordinate or in a rectangular coordinate system. This is the general equation of heat diffusion equation. Now we are going to discuss some cases. If we have a material having constant thermal conductivity, it means that we have isotropic material. Uh, for isotropic material, we can write this equation as dou square t over dou x square plus dou square t over dou y square plus dou square t over dou z square plus q over k is equals to rho cp over k times dou t over dou t. Or we can write this equation as clearly seen on your screen. Here rho Cp over K is replaced by 1 over alpha, and alpha is the thermal diffusivity, and we have learned that thermal diffusivity is the ratio of K over rho Cp. If we are dealing with steady state condition, it means that there will be no change in the amount of energy storage, as all the properties are time independent, no change with respect to time. So we will come up with an equation that dou over dou x k dou t over dou x plus dou over dou y times k dou t over dou y plus dou over dou z times k dou t over dou z plus q is equals to 0. No energy will be stored if we are going to discuss, if we are going to consider steady state conditions. Moreover, if there is heat transfer in one dimension and no energy will be generated, and we are going to consider that heat will transfer only in x direction, we can write the heat diffusion equation in a simplified form, that d over dx times k dt over dx times is equal to 0. Here partial differential is converted into full differential, or we can write that under steady state one dimensional condition and no energy generation, the heat flux is constant in the direction of transfer, dqx double dash over dx equal to 0. These are the some conditions of heat diffusion equation which are derived from the basic heat diffusion equation, generalized heat diffusion equation that we have developed in the previous slide. These are the three results of heat diffusion equation. First result is for isotropic material in which thermal conductivity is constant. Second is for under steady state condition, and third is for one dimensional no energy generation and steady state condition. And for steady state one dimensional with no energy generation, heat flux is constant in the direction of heat transfer. Now we are going to discuss heat diffusion equation in cylindrical coordinate system. This is the figure which shows the differential control volume in cylindrical coordinate system. Differential control volume is dr r d phi dz. Take a pen in your hand. This pen is in the form of cylinder. The vertical height of the pen is the z direction. The radius of the pen is the r direction, and the surface of the pen shows the phi direction. And in cylindrical coordinate system, heat flux will be minus k del t equal to minus k I dou t over dou r plus j 1 over r dou t over dou phi plus k dou t over dou z. Again here I, j, k are the unit vectors in the x, y and z direction. General here Heat flux in the r direction is minus k dava t over dava r. Heat flux in the phi direction is minus k 1 over r dava t over dava phi, and heat flux in the z direction is minus k dava t over dava z. Now, general form of heat equation in the cylindrical coordinate system is available on your screen. You don't need to go into the derivation of this equation, but you can interpret each and every term, and remember this is the general form of heat diffusion equation in cylindrical coordinate system. Now we are moving towards the heat diffusion equation in spherical coordinate system. Uh, Cricket ball is in the shape of a sphere. Now take imagine a ball in your hand. The radial direction is can be imagined that from the center of the ball to the outer periphery of the ball shows the radius of the ball or r direction. Uh, Consider the same position. The same position shows the phi side of the sphere, and the ball with smooth surfaces which we shine when we have to ball reverse swing. That surface can be considered as theta direction, and differential control volume dimensions will be dr r sine theta d phi and r d theta. For conduction analysis in spherical coordinate system, r phi and theta. R is the radius of the sphere, phi is the direction of seam in your cricket ball, and theta is the direction of the surface which we have to shine when we have to bowl reverse swing. In spherical coordinates, the general form of the heat flux vector and Fourier's law is q double dash is equal to minus k del phi is equals to minus k I dava t over dava r plus j 1 over r dava t over dava theta plus k 1 over r sine theta dava t over dava phi, where heat flux in r direction is equal to minus k dava t over dava r. Heat flux in theta direction is minus k 1 over r dava t over dava theta, and heat flux in phi direction is equal to minus k r sine theta dava t over dava phi. The general form of heat diffusion equation in spherical coordinates is available on your screen, and again you have no need to go in detail of the derivation of heat diffusion equation in cylindrical and in spherical coordinate system. Uh, with that, we have done with our lecture 3. In lecture 3, we have learned the heat conduction equation, which is the Fourier's law of heat equation. We have learned the different thermal properties of the material, and finally, we have learned the heat diffusion equation in cylindrical, spherical, and rectangular coordinate system. If you have any